Hello, and welcome to the lecture of Vision, Display, and Controls. So mainly today we're going to talk about these three topics. Let's first start from vision. So when we talk about the vision, so first we need to look at this electromagnetic spectrum. So there are different lenses of the wavelengths, and for our human eyes, the visible to our human eyes is actually very limited. It's only about 400 to 700 nanometers length. So we need to acknowledge that there are a lot of wavelengths that we cannot see, and our human eyes have certain limitations. And one concept is luminance. So luminance basically is to describe the intensity of light emitted from a surface area. So you can see from this table that one luminance basically that's one millilambert is a white paper 1 foot from a candle. So this is the how much luminance it is. And also you can describe 100 milliamperes similar to the Earth on a cloudy day, or 1,000 will be like Earth on a clear day. Well, when it gets even more brighter, and you will see that if it is 10,000 milliampere, is like when we see a white paper in a sunlight. Well, when there's a certain threshold that we can that will probably give human eyes a pen that is 3 to the power of 10 to the power of 4 milliamperes, and so that will be in this range. It will start to hurt our eyes. And also there's a threshold of detectability, and if it is smaller than 1 to 10 times 10 to the power of -6, then it's hard for us to tell or detect because of the very low luminance. And so we can use a different ways to describe the visual performance. For example, brightness, visual angle, visual acuity, and color, and also visual fields. And then these concepts are very fundamental and basic to our vision. Now let's look at each of those. So brightness, basically that's the relative amount of light reflected from an object, and you can tell from from the two pictures that even with different background, and also you can see the brightness can be described here. And next one is visual angle. So visual angle basically it can be described using 2 times arctangent s divided by 2d. So s is the length of the object, while the d is distance from the eye point to the object. You can see this is the visual angle that when you see or when you use your eye to look at one object. And here are some of the common ones. For example, a quarter at 10 feet, that is 1.5 degrees. While a car at 100 yards, then that will be 2.9 degrees. So this is a visual angle that can describe how much angle that from your eyes can see the product or the object from a certain distance. And another one is visual acuity, and so it basically this is the ability to resolve details. So oftentimes we use that to describe how small visual angle it is. And for example, one acuity will be to separate, right? To have a minimum separable gap. For example, these pictures. You And you can see some of the gap can be very large, while some of the gaps can be very small. When it's small enough, if you can still recognize that kind of a gap, or you just see it as one whole part. So this is gap resolution. And also there's a spot detection. For example, these pictures. Some with a big spot and a small spot. When a spot is getting small enough, sometimes it's really hard to detect. And also you can recognize the displacement. Like those pictures, sometimes might be easier to tell that there's a clear displacement, while sometimes it may be very small displacements. You can tell. And another one is the color in the visions. Well, something we just need to understand is there are different attributes to describe color. For example, hue, saturation, and also brightness. And also there are thousands of distinct colors in the color scheme. And but there are some of the very common ones. For example, 24 distinct colors and commonly recognized are non-common colors we see in our lives. Another concept is a visual field. So visual field means to describe, what is a field angle that a person can see. For example, with one eye, like this, with one eye, this is the angle that you can see. So this is a visual field. And with two eyes, what you can see will be around back here. So you can actually close one eye and check if it's what is your visual field. And some of the common visual impairment, and I believe a lot of those you have seen in your lives. For example, myopia, hyperopia, and also night blindness, color blindness. Another one is tunnel vision. So tunnel vision basically is a reduced field of the view. Some people might have a little bit of that issue. When you have a smaller field of view compared to other people. And when we are doing a visual search, especially doing in some inspection of the parts, something we a lot of factors we want to look at. For example, visual acuity, color vision, and also discriminability, and also memory standards and decision criteria you want to take care of when you are having some kind of visual inspection of the products. So a lot of times our human eyes actually have limitations. So that's why when you are using our human eyes in order to check the quality of the visual inspection of the parts, there are also limitations. And also, even though we can have a good control, a lot of times there are physical and also environmental factors that actually can affect our judgments, like lighting, illumination, and also noise. And a bunch of other factors that also can affect our visual inspection. You can check all these factors and think about how it can affect your judgments. And for the human machine system, basically this is a system that when the human gonna operate the machine in order to interact with the environment, and there are three major components: the environment, the displays, and also the human. The machine system, and also the human. And usually the machine system includes both displays and controls. For display, and the display is actually big topic because there are a lot of really complicated things when you are designing displays on many principles you might want to follow in order to get design very ergonomic or human friendly visual display. And the cockpit is actually one of examples that a lot of researchers have looked at because cockpit involves a lot of parameters that need to monitor, as well as a lot of controls that you need to design in order to interact with the machine. So that's why cockpit has been researched a lot in order to help pilots to operate the interface. And one kind of the display is you can tell the some different visual displays. Like one is circular or analog, or you can use digitals, or you can use this, or you can use this kind of analog. And these are just different ways of displaying values. And here are the 13 principles of display design. And we are not gonna talk through one by one, but I'm gonna pick some of the key principles and then to describe with some examples. And I encourage you to go through each one of those by yourself and then look at some examples. Either by searching some applications or examples how these are principles actually realized in certain displays, or you can just use your some of the displays in your life to see how they use those principles. The one is legibility. You want to make sure the letters or the text or the pictures on the display has good contrast and also have a standardized font size so everyone can understand that. And also you want to care about the characters size to make sure it's not too small or not too big. So it's like when you are for example, when you're designing your poster, you want to think about what is the size of the text that you want to use in your poster and make sure it's within a certain distance, right? The reader or the audience can see clearly of the text on the poster, and also it's not too big and not too small. And also the same the font size. Some of the fonts can be very easy to read, while some of the font probably requires a little bit effort in order to read. Well, in terms of the color, some of the colors might have a better illumination, while some of the color with different background might have a poor quality illumination. For example, if you use yellow on the white, right? So we can tell that how poor of the contrast it is. And also in the displays we can use different coding methods, but those codings you might want to choose certain levels that the magnitude less or equal than 2. Why is 7? So why is 7? Because it depends on our the sensory memories, right? So the more levels or magnitude you have, actually it will create a more load from our brain to process. And so some of the coding can be the area coding, some bigger area versus small area, or the line length, a shorter line versus a longer line, and also some of the number of primitives, that's 3 versus 4 or more, and also luminance. So these are clear contrast of the luminance as coding, or inclination with different directions. So these all can be different coding methods. And another principle is the use of pictorial realism. As you can tell, for some of the displays, if you use only tests, right? Or you use some of the numbers. Probably it's really hard to tell what it is. But if you show the picture, it's very clear that where the part was. For example, here in the seating selection, you can easily tell where the seat is. But if without this picture, it only gives you, say, a seat number, then it's probably going to be very difficult to tell where the seat is. And also, for a moving, display, you might want to consider some of the displays like this. Right? For example, the fuel level, you have this, this gauge, and then from low fuel level to high fuel level. I use the moving part to, for displays. And some of the displays are related to the alert, so you might want to use some of the color coding in order to create the alerts. For example, black versus amber versus red colors. And display also have some of the layout principles, and some of the, for example, you might want to choose. It depends on the frequency of the use. You might want to minimize the information access costs, and also based on the importance, or it can be relatedness. If it is some of the displays are pretty close or to each other, you might want to group them together, and also the sequence of use to facilitate the procedures. Functional grouping, also stimulus response compatibility, and clutter avoidance, and also proximity compatibility, near in-mind, near in panel. We can see some examples here. One type of the display is a head-up display. So the head-up display mainly, that is, we use a projector here, and then we use a mirror in order to create an image. Create an image here. The image actually from pilot's eyes, you can see for a further distance from the windscreen. That would be similar to this picture. So this is a very typical head-up display. And also there are some displays like head-mounted display. For example, you can use a Google Glass and to show some information in front of it. So that's a head-mounted display. And one principle is the proximity. You might want this place those controls close to the displays or control elements. For example, like this, right? If you create it like this, it might cause a little confusions. But if you choose the display like this, you can easily tell that this control is for this one, this control is for this one, this control is for this one, right? And also, you can, when you are designing a control, you want to make sure that the control is similar to the physical appearance of what you are controlling, right? For example, this is landing gear lever handle that's shaped like a wheel, and so this is a kind of a simulate the machine you are controlling. And also, you might want to think about the arrangement of the controls. And when the principle is arrange groups of the controls in the same pattern as groups of displays or control elements. So the stove is one of the examples that we have seen a lot in our lives, and some of the design might be like this. And I assume in your life, you also had some of confusions or mistakes. But if you design a controls with the same arrangement as the stove, for the controls, then it might easily tell that which control controls which stove, right? Yeah, both ways work very well. Also for the controls, there are some of the principles related to the movement compatibility. For example, the population stereotypes, up to increase, right to increase, clockwise to increase, and also various principle, skill side principle. We're gonna go through them one by one. So first, population stereotypes. So a population stereotype is basically an expectation or the habit. Group a specific group of people actually are have about how to interpret or to behave. And for example, when in most of the countries, people walk on the right hand door, right? And also if it turn clockwise, that is to increase. If it is counterclockwise, that is to decrease. Well, same with upward movements to increase. When the downward make movement is to decrease. So these are the stereotypes we can use in designing the controls. Same. So the up to increase is also one of the principles to you can use for designing a control. For example, all these control buttons. The right to increase is also, for example, the lever is also move lever to the right is to increase the temperature or the value on control. Right? If you move the lever to the left, that is to decrease the value of the control. Clockwise to increase, for example, our the volume can be controlled by turning it to clockwise to increase the volume, and then the counterclockwise to decrease the volume. So these all compatible with our behavior, our stereotype of behavior that are our habit. And so one of the compatibility is the Varick's principle. So basically, that's the principle is about the pointer should move in the same direction as the nearest point on control knob. What does it mean is, so this is this is a pointer, then this is the display, and you might want to when this knob is actually turning this direction, the same the value of display also turning this direction. This is one example, and the other one example is if we're having this, doing the opposite way, same thing. We can see this knob. When we turn the knob clockwise direction, basically it should move in the same direction as the display is moving. So this is called a Varick's principle. So the skill side principle is that when we're designing a control, and if you want to to have the control, it's similar to the one that is on a display. So we should have the same direction, right? Use the same direction of the part of our control knob. So say that if you want to decrease if you want to move the value of the display could go to this direction, then you have to turn the knob this direction. Same way with this one. And also there's a move compatibility about vehicular control. So some of the vehicles you can tell that it will be like this. In the front plane you can control the front plane, and also you can control the downward or forward here. And so you want to make sure that there's to the right or to the left. So basically it's have the same move compatibility with the device on the machine you're controlling. Right, same way when we are driving a car, as you can tell. And Also, when we are designing the control, we can also use the force to be related to displacement. So basically, the more force you use, with control, then there'll be more movement you can get of the control. It can be linear or it can be rotational. So there is a ratio you might want to remember. So that is the control response ratio. So control response means so after here that is the control movement and divided by the change in the control parameter. What does it mean? It means, so say if we only move a little bit of the control, but there is a big change of the control parameter, which means that's very sensitive, right? So then you have a really low CR ratio. But with the high CR ratio means that you move the control a lot, but actually it's not changing much of the control parameter. It means that is a high CR ratio. Well, sometimes you might want to have a really low CR ratio. Sometimes you might have a high CR ratio. One example will be the sensitivity of the mouse, right? Computer mouse you are using. Sometimes you can say, oh, that is very sensitive. That you even change a little bit, then the pointer can go a long way. Well, sometimes you might have to move along more. Well, in some of the controls, for example, if you are controlling a very small scale, for example, macroscope or even nanoscale controls at a nanoscale, then you might want to design a very high CR ratio because you don't want to just move a little bit and they change have a big change, right? Because all you want to do is have a really minor adjustment in that small scale. So high CR ratio will be preferred. So optimal or typical CR ratio for the knobs will be 0.2 to 0.8, while the lever will be 2.5 to 4. So you can use some of the values, some examples trying to figure out what is CR ratio that for your the device. And for the codings, control also can have some of the codings. For example, you can use size as codings, and also type as codings. Some of them can be used color, some of them can be used shape, or texture, or labels. Labels just simply use text to describe what is controls, or you can use locations. For example, the stove example. And in terms of the control devices, so there are some of the linear and also rotary control, and also you can categorize them as discrete and also continuous controls. So discrete controls will be that the control device or the control can only take the discrete values, separate values. It can be linear or rotary. If the linear, all these push button switches, a lever or keyboard can achieve that goal. While rotary, the same thing. You can take also. It can also take some separate values. Well, for the continuous, you might want to think about, because the values are really not discrete. So for the linears, it can be a lever or joystick or the pedal, right? For example, the car pedals, right? So start the car and also do a step on the brake. And also more often we use for continuous we use rotary ones. Use a knob or thumb wheel, crank or rotary pedal. And here's an example of the keyboard. Keyboard is a very common control device we see in our lives. And actually there are many different layouts of the keyboards. For example, this is the common one we use, and also some of the keyboards are designed this way, the A, B, C, D, E, F, G, H, I, and some of the keyboards are like this. And the calculator keyboard, the phone's keyboards are also different with some other devices. So and also sometimes you might see the keyboards like this. It's more ergonomic or waterproof. And some of the new technologies in control device will be the touch screen, which has been we use in our everyday life in our smartphones or some touch screen interfaces. And stylus is also one of those we use very often. And trackballs, you can use trackballs to track where to move the pointer and track where it is. And another type of the control device will be the voice inputs. So it brings some advantage that you do not need to physically to move something, but it brings a lot of convenience. But the problem is the voice also has a lot of disadvantages, as you can tell, right? Sometimes it just misinterpret your the meaning of what you say, or didn't really understand well, and also it requires a lot of training in order to understand correctly. And also voice input will be affected by noisy environment, or it can also bring some of the stress when you are trying to give instructions. And so here is one example about brain computer interface. You can use actually your brain to to control the interface as well. So this is one of the innovative control device people have developed. All right, so basically for this lecture, the main idea is for you to see all these different principles in display design and also control design. It's more of how to use them. I assume that most of you have already kind of recognized it when you are using your everyday life devices. For example, you're driving your car, your smartphone, or using your computer, a bunch of other devices, and you can easily tell how they are applied in your life. But what about when you are designing a display or control? How do you use those principles and make sure you can design in a way that it requires very minimum effort to to understand your display and also your interface. So it's more of a practice instead of understanding. All right, so that's all about this lecture.